Hi, this is Dan Bowen, your friendly neighborhood stratospheric balloon expert. Let's continue our informal exploration of interesting balloon science papers. Ballast valve. Now we're back into the mechanics. The altitude control is an automatic ballast trapping device consisting essentially of a diaphragm-operated needle valve, which jettisons a liquid ballast whenever the balloon is below the altitude at which the control is actuated. This is shown in Figure 2. The ballast reservoir, in general, can hold 15 kilograms of liquid ballast, usually compass fluid, which is a highly refined kerosene-type petroleum product. When they say compass fluid, it was actually used in magnetic navigation compasses for ships and airplanes to keep the needle or the ball in there from swinging around rapidly. When the atmospheric pressure outside the diaphragm is 5 millibars above the internal pressure, 160 grams of ballast per minute flow under a 1-foot head. Okay, well, let's go back here and take a look at this. So the automatic ballast valve, let's zoom in here. Let's take a look at all the parts. There's a lot going on here. So here where we see it says diaphragm, normally open to atmosphere, sealed at max altitude. That is a sealed can, just like we talked about in the last video, where the air will be sealed in there, and as the balloon rises, this rippled side of the can will extend outwards. It will bend and bow and expand up and down and push these rods apart. This is a very complicated setup. So we'll just take the bits that seem obvious first. So diaphragm depressor for ground check. Well, that looks like it probably means it will artificially move the diaphragm like it had been moved if it were flying, for checking if this device was working properly before you let it go. The needle valve ballast control. So that is interesting. That may be a way for them to adjust the rate of flow of the liquid through there. Needle valves are pretty simple devices where you have something about like it's not as small as a needle, but it may be like 2 millimeters in diameter, like a little rod that has a screw thread around it, but the tip is sharpened to a point. And that point will actually, as you turn the rod, that brings the point in closer and closer to a hole until that point actually goes into the hole and jams it shut. And being able to retract the needle back and forth very precisely with that screw thread around the needle allows you to control the flow of liquid or gas through this hole, effectively performing what a throttle would do. It becomes a throttle valve. So we see here up at the top the ballast inlet tube. That must be where the liquid reservoir drained through down into this ballast device. So ballast discharge tube. It looks like, let me see if we can make a little drawing on here. Let's see. Let me do this. It looks like the ballast would come down through here, through the valve, and then out over here, and then drain down outside, like that. So it would come in through here, go through the speed-reducing needle valve, and the actual diaphragm would be opening and shutting the valve here. So let's go ahead and clear that. So we see ballast discharge tube, needle valve diaphragm seal. That's interesting. So we have another sharpened rod that approaches a hole. And it looks like there's some little springs here and here. And those look like they're pulling up on this little plate. And we can imagine that there's a needle that might be pointing upwards. And it says it's a diaphragm seal. So that would lead me to believe that that needle is going to stop the diaphragm from having an opening to the outside world. Indeed, it says diaphragm seal-off mechanism. And so we have a squib. These squibs are wonderful devices. They are a pyrotechnic system where you can apply electric power through these wires. And when you do, there's a little igniter in here that sets an explosive charge on fire. And when it does, the little explosion drives a little knife forward through this cylinder, and it stops at the end. And the knife will cut right through this string that is actually going down through the center of the cylinder of the squib. Now, in this old-fashioned drawing, the squib is shown cut away, but it is actually just a round cylinder with a little hole drilled through it for the string, and the knife will come straight across, passing through the string and crashing into the other end. And the goal of this is indeed to cut the squib electrically, to cut the string with an electrical pulse. And it looks like the little string is a restraining cord for the diaphragm seal-off mechanism. So it looks like if this squib fires that knife, cuts the cord at the maximum altitude that the balloon reaches. So when the balloon gets as high as it's ever going to go the first time, this fires, cuts the cord, and seals the diaphragm shut. So what that means is the diaphragm has just been resting and not expanding or contracting as the balloon climbed because it was not sealed. The air inside was able to slowly leak out as the air pressure dropped outside in its climb. But now that it's reached maximum altitude, it's no longer going to be able to move in or out. So we'll see what the consequences of that are in a little while. So we see here another reminder of that it is normally open to atmosphere and sealed at max altitude. And by the way, in this old-fashioned drawing of the squib, they refer to the knife, I believe, as a cannon works. When the atmospheric pressure outside the diaphragm, that's the little sealed can with the flexible sides, is 5 millibars above the internal pressure. Let's go ahead and convert that to pascals. So we're always using a common unit set for our discussions here. So 5 millibars is 500 pascals. So when the pressure outside the diaphragm is 5 millibars above the internal air in the diagram, 160 grams of ballast per minute flow under a 1-foot head. There's a lot to unpack in this sentence here. Well, let's start at the end. A 1-foot head. This paper is full of old, outdated scientific references. So when they say 1-foot head, what they mean is the liquid is like the top of the liquid. If you start from the valve and you go all the way to the top of the liquid sloshing around in the tank, that will be exactly 1 foot from the valve to the sloshing surface of the liquid above. That's what head refers to. And that implies that the weight of the liquid at this much height, basically this much of a pile vertically of this substance, will exert a certain amount of pressure at the bottom of that 1 foot you can imagine like a straw, a drinking straw. If you had one 1 foot long, there's going to be a certain amount of weight of that liquid, which is going to be basically represented as water pressure at the bottom of this tube. So if this were water, we can actually compute what that liquid gravity pressure, also called head pressure, would be. So in my converter, I'm just going to type in the inches of water section, because we can just use this as 12 inches of water for 1 foot. And that converts to 3,000 pascals. So the liquid, as it's being held back by the valve, is at a pressure of about 3,000 pascals. And when the valve opens, they have measured that 160 grams of this liquid per minute will flow through that valve when the liquid is full to 1 foot above the valve. When the automatic ballast valve is wide open, which is after 6.5 millibars increase over the internal pressure. Let's see, what is 6.5 millibars? 6.5. That is 650 pascals. Well, I should remember that. You just multiply that times 100 to get pascals. When it's 650 pascals over the internal pressure, 300 grams per minute flow. So as we saw before, this needle valve up here, remember I said it could be used for throttling the flow? It apparently is being used exactly for that. This one up here that says ballast control, let me highlight here. There we go. This one here, which is actually right around here at the elbow of the flow of the ballast. As the diaphragm moves up and down, the needle moves closer to the hole or farther from the hole. And when the needle is farther from the hole, it allows more liquid to flow through, or to flow through faster. And when it's close to the hole, almost to jamming it shut, the fluid obviously flows slower. So they're actually using this to give you an adjustable liquid ballast dropping mechanism, which is pretty slick. So let's see. The reason why they're talking about this diaphragm having external pressure above the internal pressure is because of what happened at the maximum altitude. When the diaphragm was shut by the squib at maximum altitude, it trapped the air pressure that exists at that maximum altitude in the diaphragm. And from then on, if the balloon sinks downward, the diaphragm is going to be crushed smaller and smaller as the top and the bottom sides of this round can, this little disc here, which I will highlight again. This disc here, it's shown in a cutaway, but this is actually, I'll just sort of trace around the sort of theoretical shape of this here. It's this angled bit is a cutout, and these lines, these circular lines, are ripples. And this is actually, the two sides, the top and the bottom, are going to collapse towards each other as the air pressure outside gets higher than the trapped air pressure inside. So as the balloon sinks, the diaphragm collapses and pulls the needle down away from the hole in this tube. It's a very elegant system. So the farther down the balloon sinks, the faster it starts dropping weight. Just like a hot air balloon. Okay. So the values they're talking about of 160 grams per minute or 300 grams per minute may be compared with a diffusion loss on the order of 10 grams per hour. So what that means is The diffusion is not a problem. It's not even really a factor. It's less than 1 gram per minute. So they don't have to worry about diffusion in this whole setup. Efforts are made to cause the static rate of leakage, i.e. the leakage which proceeds when the automatic valve is closed. They're trying to make it leak all the time, a little bit. The amount of weight lost through those drips slightly compensates for the helium loss from the balloon of 10 grams per hour. It would basically mean that your balloon will fly level and not have to sink all the way down and then back up and down and back up because of the 10 grams per hour diffusion loss. There's a footnote. So things have been simplified since this paper was written. Only a fixed simple leak is used for daytime flights. During the day when the sun is out, your balloon's not going to sink. So they just let this drip along and it keeps the balloon at its maximum altitude. I've actually done that for an amateur flight before by just poking a tiny little hole in a bottle and hanging it on a balloon, filling it with alcohol. Let's see, the automatic ballast valve is used alone for flights through sunset or sunrise. That's all for today. Be sure to like this video, share it with your friends, and subscribe to the channel.